So I'm Anthony Fowler from the University of Newcastle in Australia, and in this presentation I'll be describing some recent work we've done involving the design and characterization of a novel 3-degree freedom MEMS ultrasonic energy harvester. So as we know, energy harvesting is basically the conversion of energy from an external source into electrical energy to power some sort of electrical system. So this can take place on a wide range of scales. On a macro scale, this might involve harvesting energy from motions of ocean waves, buildings or bridges, to feed power back into the grid. On a microscale, this might involve providing power to smaller devices such as wireless sensor nodes, portable electronic devices, or biomedical implants. And so these devices usually run on battery power, which means they only have a limited runtime before they need to be recharged. So it would be a clear advantage to be able to design a microscale device that can be integrated into the system to harvest energy from external sources to help increase its runtime, or even to allow it to become self-sufficient. So we've been doing some work on using microelectromechanical systems, or MEMS, for energy harvesting applications. So a clear advantage of using MEMS for this sort of application is that we can often integrate the MEMS harvesters directly into the device that they're powering. So a range of energy sources have been used for MEMS energy harvesting, including solar energy, thermal energy, radio frequency EM waves, and vibration energy. And due to the fact that low-level vibrations tend to be prevalent throughout the environment, even in the absence of other forms of energy, this has tended to be the most popular focus point for as an energy source for MEMS, energy harvesting. Our research group has recently been looking at the use of MEMS for harvesting energy from ultrasonic waves rather than external vibrations. A motivating factor for this interest is the idea that in the future, biomedical applications such as patient monitoring and drug delivery are expected to increasingly feature implanted electronic devices within the body. So RF energy has been demonstrated to power these sort of devices. However, there are still challenges in safely and reliably supplying power to devices that are implanted within the human body. And so a MEMS-based ultrasonic energy harvester represents a potential solution to this problem. So an example application would see a MEMS harvester integrated into a device that's to be placed inside the human body, such as a pacemaker or blood pressure sensor, and an ultrasonic transmitter could then be placed above the surface of the skin to emit ultrasonic waves through the body towards the device that will induce a mechanical resonance in the system. And this mechanical displacement can then be converted by the harvester into electrical energy that can be used to help power the system. So we previously demonstrated a 2-degree freedom MEMS harvester based on a silicon and insulator-based fabrication process. So the device features a central proof mass which is designed to absorb incoming ultrasonic waves, and it's connected to a series of flexures that allow the mass to resonate in the in-plane X and Y directions when an ultrasonic transmitter is used to excite it. So the flexures surrounding the stage are designed to allow it to have mechanical resonant modes and at the frequency of the exciting ultrasonic waves in order to maximize the displacement of the system. Then to convert these mechanical displacements into electrical energy, the device features electrostatic transducers located around the edges of the device. So in this system, the electrostatic transducers take the form of in-plane comb finger variable capacitors. So one electrode of each of these transducers is connected to the substrate, while the second electrode is connected to the proof mass. So if this is an external bias is used to provide initial charge to this capacitor, then the displacements of the mass can be used to vary the capacitance of the structure and used to increase the energy stored on it. So in the testing of this characterized device, we found that the frequency response of the system showed that the resonant peaks are pretty close to 40 kilohertz. And we chose this frequency as this is a frequency which we can readily buy off-the-shelf ultrasonic transmitters. Then to test the power output of the device, we connected a diode-based rectifying circuit to the output of the electrostatic transducers in order to convert the AC outputs into a DC output that can be used to charge a capacitor. So based on this testing, we found that over a period of time, on average, the device was able to generate around 21 nanowatts of energy. So recently we've extended this previous work by designing a new MEMS-based system that has 3 mechanical degrees of freedom, and that it has mechanical resonant modes in both the in-plane X and Y axes as well as the out-of-plane Z-axis. So the operation of the device in the in-plane directions is essentially the same as the previous device, in that there's a large central mass structure surrounded by a series of flexures that allow the mass to vibrate in the in-plane directions. And again, we use electrostatic transducers to convert mechanical displacements into electrical energy. But the main new feature of this device is the way in which we create mechanical out-of-plane resonant modes. And so this is done by modifying the structure of the central proof mass. So in the previous device, this was just a simple block connected by flexures at the corners of the device. But in this structure, we've subdivided it to include these 4 submasses, which each feature their own flexure mechanism, which is connected directly to the substrate. And so this is designed to allow this submass to resonate in the out-of-plane direction at the desired frequency. So variable capacitors are formed due to the overlap between the comb fingers on each submass and the fingers on the surrounding structure. So effectively, each submass represents one electrode of a variable capacitor, and the surrounding structure represents a common electrode for each of these 4 capacitors. And again, each of the resonant frequencies of the device are tuned to around 40 kHz due to us using ultrasonic transmitters of this frequency. So these simulations show the resonant modes of the system. So in the in-plane directions, the whole central mass structure moves in unison, but the out-of-plane components involve just the relative displacements between each submass and the surrounding structure. So the device was fabricated using the commercial metal mumps process by MEMS in which the proof masses, the flexures, and the electrostatic transducers are fabricated from 20 micrometer thick electroplated nickel. So the previous 2-degree of freedom system was fabricated using a silicon and insulator based process. So we've used this nickel-based process as it allows us to use these extra polysilicon and silicon nitride layers, which we've used to create the out-of-plane harvesting mechanisms. But a significant disadvantage that this process has over the silicon and insulator-based process is that the minimum feature size of this is 4 times larger than the SOI-based process at 8 micrometers, which leads to a much lower comb finger density. In addition, the minimum gap size between structures is also 4 times larger, so we get much lower changes in capacitance with the proof mass. So in the testing of the characterized device, we first applied ultrasonic waves of the device in order to find frequency response along the X, Y, and Z axes. So these plots show the experimentally obtained frequency response when a 100-volt DC bias was applied to the device's electrostatic transducers. So we found that the resonant peaks of the system are all located around 36 kHz, which is slightly lower than the 40 kHz design frequency, most likely due to variations in the fabrication process, such as thinner than desired electroplating resulting in thinner flexures. So we also wanted to mechanically verify the mode shape of the out-of-plane mode, which we did using the vibrometer for microsystem analyzer. So we used it to perform a scan across the surface of one of these submasses while actuating the device with a wideband chirp signal using the ultrasonic transmitter. We found that it's pretty consistent with the simulated mode shape from Conventorware. And again, the frequency was at the 36 kHz frequency we found from the previous electrical frequency response. So we also looked at the power output of the system using the same diode-based rectifying circuit that we used for the previous 2-degree freedom system. So the device had its electrostatic transducers biased with 100 volts DC, and we used an ultrasonic transmitter being driven by a 36 kHz signal, which was the frequency of the identified mechanical system. And then we connected a 1 microfarad capacitor to the output of the rectifying circuit to calculate the harvested energy. So we found that based on the evolving voltage, we calculated an average power output of around 12.6 nanowatts. So this is lower than the previous 2DOF system. However, as I've stated, this is most likely due to the limitations of the chosen fabrication process. And we're looking to optimize this system in a future version of the device. So that's in my talk. Thank you.